In this video, I'll help to clarify certain doubts. The first doubt is encirclements. Alright, what is actually encirclement? Alright, and often there is a careless mistake in this understanding. Second one I want to go on is the determining of the stability. Alright, and we often use this formula in the previous video, right? And then it must be talking about closed loop transfer function. Okay, it must be talking about closed loop transfer function. And then four, now to start, I'll just start off with what is exactly encirclement. The encirclement, the definition of it is that when your Nyquist plot, alright, loop around -1. Alright, when it loops around -1, this means n is equals to 1. Okay, if it's clockwise okay, if it's clockwise, n is equals to 1. If it's anti-clockwise, alright, going this direction, then it's -1. Alright, this is what we have said. But I just want to define clearly that this is one loop. Alright, this is one loop that loop around -1. Okay, comparatively, if I have something like that, this is two loop. Okay, it's because I have a somewhat exterior loop, as you can see. I encircle it one loop, and within it I encircle it another time. So this is why I encircle 2 times. Alright, but however, for me, I don't know whether for you, but whenever I saw this, I will assume that the encirclement is only this thing. So it's just encircling one time and that's it. I thought it was like that. So often I make a lot of careless mistakes due to that. Alright, so the encirclement even for this is -1, because the reason why I didn't actually look at this thing as an encirclement is because often in Nyquist plot there is something like that. It's also going in this direction. Right, this is just a loop. This is totally similar and that right, the loop style. Alright, while this loop didn't encircle the -1, it didn't eat the -1 inside it. Or it didn't so-called, I think you get what I mean already. So therefore this is one key understanding, alright, is that this thing doesn't mean that it's one loop. This thing means two loop. 1, 2. Okay, I just want to hope that this is pretty clear for your future mistake if you might also have this type of careless mistake that may occur. The next thing that I'm going to talk about is determining stability. In a closed loop system, we are often talking about the response because we don't want our response to go to instability. Instability means that in the Nyquist contour, it is in the right half plane. Alright, this whole green color one is the Nyquist contour. Alright, if you have any poles and zeros as in the response, which is if you have any poles and zeros inside this response, alright, or inside of this response that is inside this Nyquist contour, then this means it's unstable. Alright, so we want our output for any zeros, number of zeros and number of poles to be outside of this contour, so be somewhere over here. Okay, and therefore the z is the number of zeros that is within this contour, is to calculate how many zeros within this contour. Alright, and number of poles is simply how many poles within this contour. If I have a pole that is here, p is still equals to 0. If I have another 2, 3 pole over here, p is still equals to 0. Okay, I just want to make clear this concept. If I have just one pole over here, within this loop I'll have p equals to 1. Straightforward. Okay, I'm going to debunk the fact, that there's a radius of -1 over here. Right, in the previous understanding I thought that if there is a Nyquist contour over here, Nyquist plot, sorry, anything within this is considered stable, anything over here is unstable. Alright, this understanding is wrong. Alright, from here the Nyquist Stability Criterion states if there is any z, alright, number of 0 larger than 0, this means it's unstable, and that's it. Alright, and so therefore this is just the understanding. So if I have, so this is the radius -1, right? If I have a system like this, clockwise direction, I have 2 poles over here, what can you say? Is this system stable? definitely this system is not stable. Why? It's because P is equals to 2, which is inside this right half plane, right? And although there is no encirclement, but the equation itself 0 plus 2 is equals to z equals to 2, and therefore this doesn't satisfy this requirement, right? If z is larger than 0, it's unstable. So this z is equals to 2, and therefore this is unstable. Alright? And therefore not necessary in terms of Nyquist plot itself. It's talking about the bigger picture. It's talking about all those things that can determine whether things are stable or not. If I have something like this, right, let's go in this direction, okay, and I have a pose over here. Is this system stable? Alright, are there any encirclement on the negative one? If you take a look, it's going in this direction. It didn't actually engulf the negative one, right? And therefore n is still equals to 0. P is equals to 1, 0 plus 1, z is equals to 1, which is larger than 0, unstable. So this whole thing is also unstable. Okay? Next, what about this? Is this stable or unstable? If you think about it, this is in fact stable. Why? N is a clockwise encirclement. Alright, if you take a look, this thing is looping in the anti-clockwise. If it's anti-clockwise, then it's in terms of negative. Alright, and it's looping one time. So n is equals to negative 1. There is no pose in the right half plane, therefore p is equals to 0. And therefore, n is equals to negative 1 is equals to z. And negative 1 is actually lesser than 0, and therefore this whole thing is stable. Okay, next question. Now, is this stable or not stable? You may see a lot of looping, right? But take a look. Again, this is anti-clockwise. How many loop? Alright, maybe I should use another different color. One loop. Alright? Or maybe the larger loop. 1 loop, 2 loop, and the 3 loop. So there is 3 loop in the counterclockwise, and therefore it's minus 3. Are there any pose? No pose. So therefore minus 3 is equals to z, and therefore it's lesser than 0, and this is why it's stable. Alright, and therefore if I keep this, I add in 3 more poles inside the right half plane. Is this stable or not? And in fact this is stable, still stable, because n is equals to minus 3, because we have proved that it's anti-clockwise in terms of 3 loops, 3, right? 3 loops, and p is equals to how many? How many inside the right half plane? 3, right? Therefore this is 3. So minus 3 plus 3 is equals to 0. So it's still lesser than 0, or same as 0. Alright, it didn't go more than 0. So therefore it's stable. The last one, very last one. I have something like this. Is this stable? Maybe I have a few poles lah, okay? Few poles. Is this system stable? Maybe I should put also the clockwise. Is this system stable? What am I talking? Yeah, but is this system stable? And in fact, this system is not stable. Why? N is how many? In this case, it didn't encircle minus 1, correct? It's always encircle something in the thin air, right? So therefore, it's equals to 0. Alright? But however, we have a pole over here is equals to 1. Therefore, 1 is equals to z, larger than 0, therefore unstable. Okay, lastly, this is an additional concept that I think is pretty much helpful, is that this n, okay, represents the Nyquist plot. This p and the z represent the Nyquist contour. So how do they related? How are they related actually? Alright, if you remember back, alright, just to recap, is that if I were to go in this direction, alright, my Nyquist contour is going in this direction. Alright, this is in terms of a clockwise direction, for example. Okay, the first point that I plot over here is being mapped over here. Second point I plot is being mapped over here. Okay, and this point that I plot can also be mapped. Somewhere over here. Alright, any point on this plane, alright, it's somewhat mapped into all this plot over here. This is exactly the meaning behind the mapping system. Okay, therefore if we'll just take a look.
This example shows how to create a Nyquist plot when there are poles on the geometric axis as shown at the left. We start in the normal way going up the geometric axis, but then we do a small detour around the pole on the axis. And here you can see that the detour around the pole at J4 is shown in yellow at this point here. And the detour has an infinitesimally small radius. On these plots it's exaggerated a little bit so it can be seen. But you can see here that as we do a detour of infinitesimally small radius in the counterclockwise direction in S, that the path in L of S becomes a semicircular path of infinite radius in the clockwise direction. That is the opposite direction.
Eventually you have something like this. Okay, and do you think this system is stable or not? This system is stable. Okay, this system is, in fact, this is -1 over here. It didn't encircle it, it actually cross path. It actually move in this side, and then move in this side, and then it goes all the way, and then it goes all the way like this. You see, it actually move away from the -1. So this system is stable. But you may wonder, what the hell is this? Why are there a 0 in the right half plane? Now that's the confusing thing already, right? Because this graph is for the open loop system, and this is also the reason why I say we are talking about closed loop system. The closed loop system is the response, alright, while the open loop system is simply when you input into your system. Alright, for example, your open loop system, as we can see, is this one, right? This is open loop. S+2, S-1. Alright, S-1 now, you know there is a negative zeros and negative poles. Right, it's all over here. The poles, they are all plotted over here, right here. So you're actually plotting just the so-called the open loop poles and zeros. But when you close the loop, meaning you're gonna have this out of S, close the loop, what do you have? If you remember, if you close the loop already, alright, the response is straight away plotted in the Nyquist plot. While you can straight away solve for the poles by using the characteristic equation, right? The bottom one. For example, this is L, 1 plus L. Right? So 1 plus this characteristic is the closed loop transfer function poles. And then you just solve for it. Eventually, as you can see, your poles eventually become so-called stable, right? The roots of this poles in the end is all positive. Alright? S plus something, alright? So whatever, so for example S+2, okay? S+2 is equals to 0. So what makes this poles equals to 0 is -2. And therefore, this poles actually moved. Alright, this all this position, as you can see, this positions, these are the poles and zeros, right? They actually moved. They moved to the left half plane. They actually move. So the end result is that we have something like this. We may have, because I didn't calculate, but we may have something like this in the left half plane. And this case is the closed loop now. You actually move the poles and the zeros from the open loop, which is what we have seen over here, these are the stuffs, into just now that picture over there. Alright? Somewhat like that, okay? So this is the response plot for the contour. Contour is not same as Nyquist plot. Okay, contour is just the S domain. Nyquist plot is simply the transfer function domain, and that's it. Okay, and this response, these two response now, is for the response that we have often used just now in our examples. Ta-da! Okay, therefore we can also conclude that the Nyquist, alright, the Nyquist contour, you can start off the open loop with with a zeros and poles in the left half plane. Open loop. Okay. As long as the closed loop does not have z larger than 0, alright, then it's considered unstable, right? And therefore this is the, straight away come back to the Nyquist Stability Criterion. And this is the end of this whole playlist, I would say. And goodbye.